a different language, Arabic, French, whatever language I can understand, go ahead and use it. But I will be using English for giving the lectures. So my name is Adam Bloom. I'm Algerian. I've been I graduated from University Constantine in the 90s. Did my PhD in France, Compiègne. Then I moved to the Netherlands, where I joined the computer architecture group, Parallel, and then I worked at the university as a researcher. And I'm also at what we call the e-Science Center, the technology lead at the e-Science Center. I also do a bit of research for the e-Science Center. Basically what we are doing, we're supporting application in different domains. So to make them, allow them to scale their application and take advantage of the infrastructure available in the Netherlands. So as I said, I'm located in Amsterdam, and I frequently come to visit Algeria every summer. So if we, after this lockdown and we have the chance to see each other, I will be in Algeria in the summer 2022, if possible. Just to get things clear, this course is really not really going to dive into the details of the material I'm going to cover. I'm going to give you a, we should look at it as a beginning, but not as the end. Just to introduce you to the concepts of parallel programming, big data platform, cloud computing, and Spark. And then I will do this by introducing certain concepts first. And today is going to be only these concepts. So these are the topics I'm going to cover. I mean, if you know these already, so probably you're attending the wrong class. So I don't want to disappoint you at the end of this lecture. So, but if everything in this list is clear to you, so you have to reconsider really attending this course, because this is basically what I will cover, and I don't want to waste your time more than you need to do it. Okay. So this is basically the content of today. I will talk a little bit about high performance computing, supercomputer, and how what is a speed up? How can we really speed up our programs, and what could be the parameter that will have an impact on our programming, and how can we write parallel programs? What are the different paradigms we can use to write parallel programs? But before I start, I would like to do a little bit of explain the landscape of a computer system and how can we use them, and to use them for what. So usually what I suggest to students, my students at least, I say, if you can solve your problem on your laptop, just use it. Don't go and really look for complexity. So if you, the more you go try to use bigger system, the more problems you will have to solve. And believe me or not, I mean, the most challenging problems are not technical. You can be very technical, write a good program which would work, but there's a lot of administrative problems that will face you, and you will block you and will prevent you from using the system. And the more you use bigger system, the more these administrative problems will become bigger and more important, and will be more challenging. So don't think that only technical part is going to solve your problem, but also all these characteristics. Because on your laptop here, on your desktop, you already have a bit of computing power, which allow you, if you're using it correctly, to do certain bit of scaling. I think these days, most of our laptops, desktops, they have multi-core systems on them. So they have the CPU, one CPU, in general, one CPU with 8 cores, 16 cores, depending on the CPU you have on your machine, and you can do a bit of parallelism in your machine. But unfortunately, for a number of applications, this is not enough. I mean, we can have, we are not, we don't have infinite amount of storage. We don't have an infinite of CPU. And solving big problems, especially in science, I guess I hope we have in this audience, we didn't have time to check. We have maybe some physicists, some astrophysicists, some chemists who really do large simulations, and that's no way you can never use your computer to solve this problem. So your first option is to have access to a system like this one. So it's something, it's a kind of cluster. It scales a little bit. You have a little bit more nodes, a little bit more RAM and storage, and you can do a bit of parallel programming on this cluster. This is a solution. No, not everybody is able to afford this kind of clusters. They cost money. I know that Algerian universities, they have similar clusters distributed all over the universities. And one way that has been studied for the last 20 years is how can we aggregate the computation power, which is distributed and solve big problem. And that's what we have seen in the 90s, in the 20s, known as grid computing. So we can combine these things. And usually this is quite already a challenge, because usually when you develop a parallel program, you do it on your desktop. And by just porting this step and going towards this big machine here, you have sometimes to really do a lot of things, because you make some assumptions on your the infrastructure. It is here, and then these assumptions are not correct, and you have to re-engineer your software. And this is why sometimes a bit of software engineering in your code is good, because this will help you to redo everything from scratch, and you can progress in your work. That's basically what it is. But often these systems are, I would say, administratively, they are easy. Usually they are maintained by one or person who is likely to be your friend or someone from your department. And you can ask him, and he's willing to change the configuration of the system to make your system give you more performance. And that's the idea. That's a typical case. So if you don't have this opportunity to have a cluster next to your department, so you will have to go to big data centers. So that's and if you go to big data centers, you will have more problem here. So you have more computation power, more storage, but usually they are more strictly managed. This is why the person, it is not anymore a person, it is a team of administrators who are managing the systems. They have a large number of users, not only you. So you're just one out of 100 or 200 users. Yes. That is. Yeah. Sorry for the interruption. So as I said, there's a kind of infrastructure, but it is really strictly maintained. And this is the how should I say this? The most important characteristic for those administrators is not performance per user, is a kind of an average performance of the system, but is more security. These guys are concerned by securities. So if you have a system like this one, the guys who are maintaining the system will be basically blocking everything, and just by a firewall, they're just allowing a single entry point to the system in order to make sure that the system is secure. And this kind of configuration is not always nice for your application to get performance. And those guys, they will never change their mind or change the configuration or install something on the system which might compromise security or might compromise the use of different users. So this will be one of the major challenge you will be facing when you try to run your program on these machines. Okay, so but again, to take your program from your current laptop or your machine to the cluster to this one is a big step, and you have to learn some methods, technique like MPI, OpenMP, which will allow you to use concurrency and parallel programming to take advantage of those machines. I mean, if you think that just taking your code and just running it here, it will give you more or less the same performance, because if it's sequential, it's going to be sequential on here and also on here. So you have really to do a bit of parallel programming, and that's what we will try to do. But actually, sometimes even these big machines are not enough to solve problems. So we have to go and start looking for aggregating computation power across different data centers. And this also, especially for big problems, this is also possible. You can do it yourself if you're well skilled and have a lot of skills, and then you should be able to make yourself, I mean, through this kind of narrow way of connecting these machines. That's possible, but it's very difficult. But hopefully the research community for the last 20 years, I think since the 90s, they start thinking about how can we aggregate such a computation power to allow people to solve bigger problems. Yeah, and not always get stuck and just wait for months or years before they get some results. In the 90s, they came up with a very simple idea, and that's the idea of grid computing. I'm not going to cover it in these lectures, but if needed, we can talk about it. And these grid systems basically were designed to allow the computation power, which is distributed over research centers and universities, and aggregate them as a unique big system to solve the biggest problem. And one of the most known problems that have been solved by the grid, if we have physicists in this audience, they will let us know, it's LHC, Large Hadron Collider problem. So the experiment was done in Switzerland, somewhere here in Switzerland. And they have their accelerator, they accelerate particles, and they generate petabytes, terabytes of data. And this data is stored all over Europe and also all over the world. And then physicists from different parts of the world, they just go and just do the experiment. And those was solved by applying grid technology to solve this kind of problem. This is the most known application of the grid systems. Grid systems have been very popular from the 90s up to the mid 80s, sorry, mid 20, 25, 26. And then after that, they start to become less popular, not because they technically they were not good. Actually, the approach of a grid system is very, very good, well engineered. And I've been through different type of phases, first phase and second phase, but just because they were not meant to create money. So it's more research oriented to solve big problem, fundamental problem in mathematics, in physics, in chemistry, these kind of things. There were no business model that could be built around the grid technology, because the approach of grid is basically trying to be nice to these systems, because we know that we are a system, we are going to fight with these administrators, and the administrators will never give you full control of their infrastructure. So the grid has been designed to be non-intrusive and very gentle. So that means when a job goes into the system through these narrow corridors, then here it becomes part of under the control of the local administrator. And if we are in such an environment, there's no way you can guarantee things. You never guarantee that your jobs will be run in 1 minute, 2 minutes, or maybe half an hour, or maybe have to wait a couple of days before it gets to the job. And because of this uncertainty, there's no way to guarantee and there's quality of service to the user, but still you can run your job. That's one of the limit of the grid. There's after 2007, 2008, and then the cloud systems start to appear. They are more, I would say, more scalable and more easy to maintain because they have decided to go with a different approach. So the approach between differences between grid and cloud is related to the fact that here we said, okay, no central control, every institute has its own resources, and let's use them. So you can imagine that at a certain time, an administrator can decide to shut down its center, then the resources are gone. So what are you going to do with your jobs? Are you going to stop them, run them again, restart them somewhere else? In cloud, we have more, we came back to centralize the system, and especially if you talk about public clouds, the one you are using these days, like the Amazon cloud or Google cloud or these kind of clouds, they are really under the control of Amazon, Google, etc. And they can really guarantee that when you submit a job or request a virtual machine, it will be started as you wish, as you have paid for. Because here you're paying money. Yeah? Here we are using money to get those resources. Here we don't pay money. In the grid, we just become part of the grid. Actually, I think there's also the Algerian grid, where everyone who is associated with any of the university in Algeria should be able to access without having to pay money for it. I don't know if it is operational at this moment or not, but I know there were a couple of projects where the Algerian grid was also set up at a certain time. The other difference between the grid and the cloud is the way we're going to run the jobs on the different system. On the grid, we're going to go with from what we call, I call abstraction. So the grid is just a layer of software which is sitting between you, I'm talking you here, I'm thinking that you are a developer of applications, and then offering you a nice API to make sure that your job gets from the place where you are running. So from your laptop gets to the grid. The data also is moved to the grid, and they are processed. The data is moved back to another system for storage or for archiving, or back to your system to be used. So that's it. So if a job goes to a certain machine, all the dependencies that are related to the job are also supposed to be there. And if those dependencies are not installed, or they will create some bit of conflict with our library, then your job will fail. And then even in production environment grid, there's a high percentage that a job submitted on the grid will fail. And we have to, of course, retry on a different machine. But this creates a big set of problems that need to be solved, and usually that's not always easy to solve them. On the contrary, the cloud system has opted for virtualization. When I'm virtualization at this moment, we will talk about virtualization later on, you see it as if you take all your library and all your dependency with your job and take them in a kind of black box and then move them around and put them on a machine. And because everything is packed together, so there's highly a chance that this job will work and will run as expected, to the contrary to what we have seen with the grid system. And that's gave, I mean, we see it today, a lot of business are moving towards cloud systems. We have the entire world actually today is using virtualization, from Netflix to watch your movies, to read your emails on Google Mail, or Dropbox to solve your, to store your data. They are all using virtualization and cloud systems. So this is basically the landscape of the computer system that you will have to use to solve your big problems. And then you have just to choose which solution is best for you. Some people will tell you that grid is dead. No, the grid is not dead. Grid is still life and kicking. As I said, physicists are really oriented toward grid systems. So if you are a physicist, probably you will encounter a grid system being installed, and then you can use them. Maybe for free, because you will be part of the virtual organization for physicists, and then you just get access for free for that. Otherwise, you can also opt for money, and you pay for money and get some resource from cloud providers, and we will see later on how you can make use of this. I hope I made it clear that this is more or less the landscape of the infrastructure, but I want to go a little bit further in talking about the infrastructure. But before I start, I would like to give you a very simple example which illustrates what can you gain from parallelism. So let's suppose we have a sort. Everyone, I think, in this audience has maybe in his first class about programming has had the assignment from his teacher or from to implement a sort program. You sort. You have a list of numbers from 1 to 10, and you would like to sort them from 1 to 10, from the smallest to the biggest, or the way around. So let's suppose we have 1 terabyte of data. 1 terabyte of data, and we need to sort this terabyte. How much time does it take? We're going to make some estimation. It's not my calculation. I just took them from, I think, the paper from, if I'm not mistaken, is the Google paper where they really introduced the first time MapReduce. So they made these very assumptions. So we suppose we have we can read data from disk at a speed of 100 megabit per second. We can write it also at 100 megabit per second. I know these numbers maybe are out of date today because we have technology has evolved. We have maybe faster disks, especially SSDs are far faster than these numbers. We take a typical algorithm, sorting algorithm. There are plenty of other algorithms, but we just take this one. And if we want to store, to sort this 1 terabyte of data, approximately we need 5 hours. So in such a machine, I need sequentially to go through all the terabytes of data, and they came up with this calculation. Again, this is not my calculation. I'm just showing you to show that's 5 hours. So it's quite a long time. Then how can we solve this problem by going toward a parallel machine? In 2008, there was actually this became what we call a challenge, and it's being solved every year and try to push the limit every year one step further. So they managed to run this kind of sorting on a parallel system, and you can see it here. I put here, they used about 900 nodes, and every node has 4 dual core processors, 4 disks, and 8 gig memory of RAM. And they managed to do this in 3 minutes. So you see the scale, how really parallelism have managed to speed up this application. From 5 hours to 3 minutes. Can we do better? I'm not sure if I don't remember what type of method they used. Probably they used maybe a bit of MPI or any other parallelism methods here to get to this number. But can we do better? Actually, Google, did better in 2012. They introduced a big data platform. This is the first one. It's called based on MapReduce. And they managed to actually to solve this problem in a lot smaller time. And I have here a link. You can watch the video. I think we can show the video if I go here. So I think if it works. No, sorry, not here. How does it go? No. Yeah, so this is what you will see if you run the video. I'm going to run it because it doesn't take that much time. These are the cores, the green squares are the cores, the CPUs. And when they are not really overloaded, they are green. When they start to get some tasks to do from the framework, the MapReduce framework, they get yellow, they're red, they are fully full speed. And they're going to try to sort 1 terabyte of data using 1,000 nodes in 3 nodes. So let's run and see what will happen. So this is just, I will start, they start running their environment. They do a bit of calibration here just to, and then they start the map function. You see it here, the map, which is the first phase of this algorithm to start your day. So they are here doing map. Okay. I made a mistake here, sorry. Okay, now you see the map is progressing 80%, 90%, 100% of the first phase of this algorithm is finished. Now the second phase starts, it's called reduce, and it's going to progress up to 100%. And after that, the sorting of 1 terabyte has been completed. Now, how much time did it take for Google to sort 1 terabyte in 2012? Is 55 seconds. So using parallelism, we managed to bring a computation or a sequential computation from, okay, so we managed to move a computation from 5 hours to 3 minutes to less than a minute, 55 seconds, which is a bit of a speed up, if I might say here. But this is like a bit motivating, but also misleading. You can never achieve this goal if you really don't use the right tool for the right things and the right paradigm for the right application. Not everything is interchangeable and easily and generalizable. That's what I want you to remember. So be careful. That's even if you hear a lot about GPUs. GPUs can be faster than CPUs, but if you don't use them carefully, they will never give you the speed up you want to do. Actually, they will be even sometimes slower than what you can gain by just using some simple architecture, and you can gain in time and even in money. So what I would like to start is, before going to the paradigms, so I'm going to start with the computer architecture. So we have seen the systems as a whole. So what is on this supercomputer? Actually, what do we have on supercomputer is very similar to what we have on our desktop and laptop machines. So we have CPUs instead of having one CPU processor, and we have a bit of memory around it, and input output. We have to solve, we have to get the data to put it in a permanent storage. That's basically it. Over the years, the architecture of, if you remember, it's called the architect von Neumann, did not change a lot. Only the technology has changed. We integrate more, so we have more integration, so we may have more transistor on the CPU, then we can have more CPUs in just one chip. We have bigger memory, we have faster memory, we can read faster and write faster to the memory. We have hard drive, now we have SSDs, we have really fast things. So the architecture didn't change, but the technology has progressed quite a lot. And the most differences between the systems we have been discussing a few minutes ago is how these elements, the three basic elements, are connected together: the CPU, the memory, and the I/O. And the way we combine this, then we have different system, and this system is suited for certain type of application, if I may say. So this is what I'm saying here. I'm putting this in a red box just for you to remember. Some scientific problems fit better as the architecture than another. So there's still some things need to be specified. I will just show you this as one of my last video. I like to use videos during my lectures just to bash something about GPUs, or maybe show you that what we can achieve just by using the GPU, which most of desktop, good decent desktop has already online. So this following demo will show you a demo related to some chemical problem to be solved from chemistry, to the boundary, find the boundary condition for a certain molecule, and then, but it was, for me, what is one interesting, it's going to be, it was run on a simple Mac Pro on a desktop, and that I will show you the difference between running on a single processor to using the multi-core of the processor with a hyper threading, and then using the GPU, and see how much fast we're going to define the boundary condition of this molecule. And then you will see the timing here. I'm not sure if you can hear the voice of the person who's going to explain a little bit what he's doing, but in case you don't see it, this is basically what he's going to show you. But be careful, and we'll just see what's going to happen here each time we're going to read. I will start running this video.
Expect from it if you were using your own stuff. And so what we're looking at here is a demo from a talk I gave at WWDC this year. And it really highlights the ability to take existing code and to move it from running on the CPU to running on the GPU. And the really nice thing about this is that it's real world code. This is from a program I work on called day job that I work on called APPS, and the software is designed to evaluate the electrostatic properties of biological molecules, so for drug delivery systems or rational drug design, understanding protein interactions, things like that. And one of the things that we have to do in this calculation initially, certainly, is when the calculation is running. One of the stages, we have to set up what are called boundary value conditions, and those portions of the calculation can be quite slow if we want to do them as accurately as we're able to. We have some shortcuts and whatnot, but if you really want high accuracy we need to do this slower method. And so what you're observing is a visualization of that portion of the calculation. And what you can see is that the calculation for setting up these boundary value problems, just getting through this one stage, actually takes some time. I think it's going to end up taking about 50 or 60 seconds to complete. And this is running on a single core, single CPU. This is all C code, sort of straightforward stuff. And we'll talk about the actual code and use this as an example later. Okay, so just getting through this once later. Okay, so about 50.
So I just want to stop here the video. So this is basically the time we get to get this boundary condition for this molecule is using C program, which is one of the most efficient programming language on a simple Mac Pro on the desktop machine. So this is the difference between what I've shown you before, the 1 terabyte challenge, which is basically on supercomputers, and we managed to achieve a significant speed up between the sequential program, 5 hours to 3 minutes to less than a minute on a supercomputer. We're going to say similar things on your simple laptops. Hey, this is a sequential using CPU on there. Let's now run it on a multi-cores, because this is a CPU, it has 8 cores, and he's going to use a technique called hyperthreading to double the number of cores. So these are virtual cores, now not real cores. So it's only 8 cores instead of 16, but he's going to use 16 threads. Let's see how much time, and you see how parallelism could be used to speed up the machine, the execution of this program.
It's 57 seconds for that thing to run. So on a single CPU. This is the 8-core Mac Pro. It's one of the Highland systems, so it actually has hyperthreading enabled, so we can get actually 16 virtual type processors cores running. So we can run this on 16 threads. We can parallelize this calculation relatively straightforward, either using OpenMP or OpenSCL. Either way, we can parallelize it on the CPU. And if we run that, you can see it runs, takes advantage of multiple cores. It runs, it does its thing, and we get pretty good performance boost, 4.8 seconds on 16 CPUs. So that's really, really good. It tells us at least that we've got a well-defined problem, a parallelized problem, and that we can get additional performance if we have the resources available. Now, what's really interesting, though, is that we can also do this on the GPU. And what we want to know is, can we get more performance and things like that? And obviously we can. But the important thing here before I show you this is that I want you to understand is that the results that we're going to get on the GPU are identical to the results that we currently get on the CPU. And I think that's probably one of the more important things is that we're talking about numerical accuracy. So basically what I'm saying is that there's no trickery, there's no mathematical shenanigans or anything going on. We're getting the exact same results. So let's run that on the GPU. The GPU in this case is the GTX 285 from NVIDIA. And let's see that. And I can do this all day. And so what you can see is we took a calculation that was running, took about 60 seconds on this system, down to about 180 milliseconds on a single GPU, a single graphics card, which is phenomenal, I think.
Okay, I think we can stop this video over here. So I hope I have convinced you that so you can get some speed up, a reasonable speed up, just on your machine. Also, that you should not always think about using supercomputers. So on your desktops, if you have a multi-core machine, if you have a graphic cards on your machine, these gaming cards, which are often you buy for your kids, are quite powerful, and you can do a lot of computation on your local machine without having to go to supercomputer. So think that on your simple desktop, you have enough computation power to do a bit of parallel programming also before going to the supercomputers, which are far more expensive and not always available to everybody. So that is more or less my introduction to, I hope I have convinced you that there is a good reason to learn how to use parallelism and why we should use parallelism. Now I'm going to go a little bit on the the technical details. So I'll start again from the architecture. It's not the objective of this course to give you the detailed course on computer architecture, but just to give you a flavor about how these systems with their complex architecture are classified and how can we take advantage of them. I'll start from a very known taxonomy, which is from the 70s or even before that, which try to classify this multi-computer or multi-processor systems. And by just knowing how we can classify them, we can also know where we can take advantage from. So if you look at the Flame taxonomy, it tries to distinguish or classify this multi-processor system based on 2 dimensions, which are the only thing we can have when we write programs. If you think about what we are doing every day, we write instructions to process data. Now, these are the 2 dimensions we have. So if we have a program is just a bunch of lines here. These are the instruction, and we in the old time, we used to execute them one by one after another, from this line to the last line. And then because we had only one, and yeah. And the data here is also, we can consider that the data is just some system, and that database or any other type, or just files, plain files, and the size of this data is so big. Okay. But we have only these 2 things to try to characterize things which have more than one CPU. Because if we have more than CPU, there is no good reason, apparently, at least up to now, we will see later on there are some limitations. Why do I have to execute this one sequentially? Why I can't do these 2 lines in parallel if I have multi-processors on my machine? And the same thing can also be applied to the data. If I have a ton of data in my database or my files, why do I have to process them one by one in a sequential form? Why don't I just start 2 processors, make one processor work on this part when the other one work on this part? So apparently, with some assumption we are making over here, so this should be also possible if you have the resources. And this taxonomy is very simple, actually. What he did, he just said, okay, there, with these 2 dimensions, we can also think about executing them in a single way or in a multiple way. And then we can start with the most basic one, which does not deliver any parallelism, and that's the most sequential part, which is if we execute one single instruction was for one single of data. And basically, this is a kind of misuse of multiprocessor system. This is basically a simple desktop. One instruction at a time, one data at a time, and everything is sequential, and it will take ages to process 1 terabyte of data. It will take 5 it was 5 hours to do the processing. But we can also think about different scenarios. We can also think about going towards this one, which I execute a single instruction, but I will use multiple data. That means if I have, let's say, 2 processors here, processor 1 here and processor 2, yeah, these are 2 hard machines, hardcore machines I have here, and I make them execute the same instruction. This instruction I call 1. I will make it be executed on this machine and also on this machine or this processor, whatever you want to call it. But I will not be processing the same data because that's use of time. They will be doing the same thing. This one, I will give data 1, which is this portion of the data, and this guy, the other guy, I will give it data 2 here. So that's here we have 2 different data here that are processed by the 2 machines. And that's what I mean by a single instruction and multiple data. And obviously, this should give me some feedback, because if I have 1 terabyte and I have 2 processors, I split the terabyte into 2 halves and give 1 half to the processor 1, the other half to the processor 2, and they should be able to finish their work in a less or faster than if I have 1 processor which has to do 1 terabyte at the same time. The other option he also thought about, if I can also think about executing multiple instructions. If I cannot do this, or for certain reason I cannot run the same instruction, I can also think about running 2 different instructions. I will make processor 1 work on the same instruction 1, while I make the other processor work on instruction 2 at the same time. But at this time, I will make them work maybe on the same single data. I will not do the parallelism on the data, but the parallelism will be on the instructions. Then I go to the last option I have. I can do both. That means I can run different instructions on different processors, and I can run different data on different processors. So that's the most complicated one. And obviously, this might be the most beneficial way of using this multi-processing system, but also maybe the most complicated way to do it. So another way of looking at this system is how the memory and the processor are coupled together. And these big systems often, they are coupled in two types of machines. So we have a processor which has a single shared memory. That means we have on one board, we have processors and we have a memory, and memory is accessed by both processors. So both processors have the same memory, they can put data there and they can read data from there. And you might ask yourself and say, this, yeah, if they have both access to the same memory, then the memory can become a kind of bottleneck because it is shared resources, and there might be also a conflict on accessing this memory. And I will say, yes, you're completely right. Then, yeah, you have to have some control over whose processor can take at certain time the control of the memory, write them to memory, and give the control to the others. There are several techniques for that. There are also systems which couple different nodes. These are typical organization of a supercomputer, and they don't share a lot. They just, each node has its own local memory, but the processor can talk to each other via a fast network. Usually faster than what you have Ethernet. We're talking about a very fast network, which allow for a certain compilation, certain executions to be done. So this is the first type of architecture. So we have a number of CPUs sharing a memory, but unfortunately this type of architecture cannot increase. So, because if you look at the list of supercomputers, we're talking about thousands of CPUs, that we can never build a system with thousands of nodes sharing in a memory in the center, because this would be dramatic for the performance, and then we would be most of the time spending the time in managing the access to the memory than doing anything else. So usually you have up to 4 CPUs sharing the memory. How can we program this? There's a way to do this. It's called OpenMP, and this allows you to program this kind of machines in a rather efficient way. The other way of the system is, as I said, we have a high-speed network, reliable network, and then you have different CPUs, and CPUs have their own local memory. This memory is not accessed to the other, so this CPU can only write to this memory or read from this memory, but they can exchange some information with the other CPU through this high-fast network. So if some communication is needed between jobs running on these two machines, they have to go through the CPUs. There is no way that the CPU can write at least directly to this memory. And actually, this is what big platforms that have been recently designed have came across. They have designed the software system that is able to do exactly what I just said. It's not possible. So it was not possible 20 years ago, but now it's possible. There are like Spark. Spark is a big data platform which is able to see this entire memory as one unique memory. That means Spark is able to access all these memory at the same time, and the jobs also within Spark, they can also do this kind of thing. Things are progressing. So just let's stay with the architecture. So we have also a kind of intermediate solution. This is also quite common in supercomputers, that you have first CPUs which are locally on the same board, and then on the board you have shared memory, and then this shared memory is connected to other blade in your supercomputer, and they communicate through this fast network to do the. So why we are using supercomputer, I think I have answered this question. So it is, we want to solve larger problem, bigger problem, and then we want to use non-local resources because we don't have them on board. Our laptop is too small to solve our problems. Our single cluster, which is next to my department, is also too small to solve my problem. We want to use other systems. let's say I really want to give concrete examples. Suppose that you are given the possibility to use all the computation power in Algeria. So I'm sure there are different universities, they have different clusters, they are medium-sized clusters. They can't be compared to what Google has, or maybe, but altogether, they have quite a reasonable computation power that you physicists, scientists, chemists, etc., are able to solve your problem with. But you have to get access to this, and that's not possible for anyone to do this. Maybe for one or two people who are really scaleful and have access to those machines and have account on those machines and know how to do tunneling and how to do all the low-level details of computer engineering, are able to run these kind of applications.
Adam, we have
yes.
10 minutes left, so do you want to stop? It seems a good place to stop and give people a chance to ask questions.
Yeah,
for the next 10 minutes.
I think I will stop with this slide because this is kind of at the end of my first part. Then I give the floor for discussion. So yeah, I have also here a nice movie. It's 8-minute movie. I really suggest you look at it, which gives you all type of applications, from science to making movies to work a supercomputer and high performance computing will make a big difference. And I think this will end up my first part, at least the introductory part to this lecture. You're right, the time is going very fast. We have only 6 minutes left. Questions?
I'm gonna unmute everybody, so will be a lot of noise. And you can ask questions. So, we're gonna, it's being taped. We're gonna upload it so people can have access to it. بس هاي اللي عندكم question, go ahead. I'm gonna unmute all of you, and you can ask questions for the next 5 minutes, and then we go from there. The next class, we'll discuss when's going to be the next one. I will be sending emails when's going to be the next one and so forth. So, yeah, so like question, go ahead. Anybody who has question, go ahead.
Again, language is not important. I mean, if you don't want to speak English or find it difficult, you can also ask your question in French or Arabic or whatever.
Or if you want to put in the chat or something.
Yeah, you can also put your questions in the chat. I'm looking at the chat right now.
Yeah, I don't see anything.
So if you don't want to ask, so I can ask. So is this basically something that was interesting for you guys? You can say yes or no, you know. Or you were expecting a different type of lecture? Again, this is just 1/3 of my slides. Unfortunately, I was a bit too slow, so I don't like this video. So in principle, my first lecture should still contains a lot of discussion about how can really, because I show you the speed up. That's basically what I try to show, that we really can benefit from supercomputing. And usually what I like to do is always to make sure that people, before getting engaged in something, they get convinced that is useful for them. And that's basically the purpose of this first part of this presentation. If you think you, as a PhD student or as a physicist or whatever, HPC is the right path for you to solve your problem, then you should continue with the rest of the lecture. But if you're not motivated, I think you should do something else. Yes, this is interesting and yeah, this is basically what I want, because that's what I think. It's especially a lot of you will have to do a lot of simulations, and simulations mostly are heavy calculations in terms of CPU, because the program itself is very complex, but also because of just the data. The data is too big to be processed on your machine. It will take you weeks or months to do your simulation on a laptop. And if this infrastructure exists and you know how to use it, and with a reasonable amount of effort from you, I don't want you to become all computer scientists or programmers, then it should give you an advantage for your work.
Adam, there's a question in the chat.
what happens when the data cannot be split because the relationship between the data. Yes, that's a good point. Actually, that's not all the data is separable. This is why I say there's no solution which says fits all size. I mean, there's no bullet, silver bullet that I can give you and it solves all the problems. There are a large number of applications in science that really could be considered as what they call, we do data parallelism because it's easy. If you are counting words, if you are doing short kind of algorithm, there's plenty of example of algorithm that we can do split on the data, but we can also do split on the instructions. So there are two. This is why in the line taxonomy, we were looking at the instructions and the data. If we cannot parallelize on the data, we can also parallelize on the instruction if that's possible. If both are not possible, then we might reconsider looking at the way we are looking at the problem. Maybe it's the wrong way to look at the problem and we have to look at it from parallel perspective. Because sometimes changing just the parallel perspective to looking at your problem can give you some room for parallelism. So parallelism is not always possible. Of course, there are parts where it is, if you look at the code and it is sequential, we can't do much about it. The data is, as you mentioned, as you say in this question, is relationship and cutting the data into pieces. I will say it's always possible to code, to cut a certain data, but there will be some disadvantages. I did not have the time to talk about communication because cutting the data will involve communication. Communication are not always good. So what you gain in parallelism, you will lose in terms of communication. So to answer this question, I would say you're completely right. This is a problem case by case. We look at the case, we see if there's a room for parallelism in the data, we look at the room for parallelism on the instruction set. If both are not possible, which this should be more the not the usual case, because what I've seen in my experience, there's room for parallelism in most of the cases. But if not, then we have maybe rethink the way we are looking at the problem and then go from a different angle where we can get some parallelism. Absolutely, you have nothing. You can just try to get the faster CPUs, because one way to increase is to have faster. This is why we increase the frequency of the CPU. You can also use a better technology. So instead of having a hard drive, which is very slow in the read and writing, you have to turn into the technology. There's SSDs are faster. So you can also go with your sequential, but at the price of having high frequency, but you are limited. We know that we cannot increase anymore the frequency of our CPUs. They are limited. We have higher disks, RAM, bigger RAM, so the system cannot have always to switch to the disk because disks are slower than the RAM. That also can give you some speed up on your program because you cannot take advantage of the parallelism. You know.
Okay, I have a question, sir.
Yes.
Okay. First of all, thank you for your presentation, and that's very good for us. I have a question. Can you give us some sample about this technology? About who use this technology? Applications or platforms or frameworks existed?
If I understand your question correctly, so the user, you're thinking the type of users for these technologies. The end users are all kind of domain. I worked with astrophysics people, so from astronomy to high energy physics, the physicists to chemists to even humanities, people who are doing history and studying geography. They are user because there's so much data, especially for those last two guys. There's a lot of easy parallelism on the data level. So if you go to application like here, they are digitalizing all the old books and the history books, and they have they want to start processing all the books that have been published over the years, middle age, etc., etc. Up to now, there's a lot of room for doing some parallelism, because I can start working on different books at the same time if the machines are there. So anyone who has a big problem should be a potential user. The difference is that the question is, I continue your question, is what are the tools appropriate for which one? So there are tools which are very low level, and they are very tricky to use because you have to know, you have to do parallelism yourself. But the more the technology is progressing and the big data is getting in, the more people are developing tools which make your life even easier. If you take the word Spark, you will never see the parallelism yourself. So you learn how to use Spark, and then you submit your job to Spark, and Spark will take advantage of everything. When it's installed, you start processing all the things in parallel. So,
okay, Adam, there's one question in the chat. Okay, let's have it the last question, then until next time.
Yeah, he said you've mentioned the Spark can access each individual memory of the nodes. So it's more interesting to use more cores or more nodes in this case. I'm not sure I got exactly the question, but I will try to answer it. So yeah, Spark is, why Spark was designed to use memory over, you want to comment on your question? Sorry, I didn't.
Just noise, go ahead.
Okay. So that's just to explain why Spark, they decided to go into this, because you have this memory which is limited on the nodes. Yeah, you have, and then all the CPUs work only on the local nodes. And if the problem is very big, and that's, I'm talking about terabytes, petabyte, not exabyte, not, they never fit in the memory. But if we look at the entire memory of the cluster, and we have a system which is able to see the entire memory as one big slot of memory, then we can have also a rather large amount of memory that we can work with. And memory are much faster than the disk. And this is why Spark is trying first to exploit the memory over the different nodes to make sure that it's as fast as possible. It's only when the memory, physical memory, reaches its limit, then Spark will switch to use disk. And here he will lose performance. And I think I will talk about Spark, as they have dedicated lecture on Spark, and explain how we can use Spark and how Spark can switch between using RAM and disk, etc. So that's becomes clear later.
Okay, Adam, Jama'a, you know, this one more question, and هذه التالية. It's good, it's very good. عندكم بزاف دي كيستيون، بصح خليهم الخطرة الجاية. I mean, go over this thing. بصح كاين كيستيون التالية آدم ماذا بك تشوفها في الشات.
Okay, it's not clear. I'm going to read it loudly, so I don't know if you see it also. It's not clear for me the difference between grid and cloud cluster, how to use computing resources on grid without central control. That's a good question. So let me just draw. Maybe here I can draw something. It's does it? Why? Yes. Okay. Yes. Yeah. So these are just names. So the cluster is the basic things. This is you start with the cluster. This is the cluster. So to program this cluster, which has number of nodes, number of CPU, GPU, but has limited. So basically, I'm going to mention a few technology. We're going to use MPI. MPI is one of the techniques used to program this cluster. Okay, or OpenMP. That's another technology used to program here. So we can also open. I don't know how to write with this, but I will try. OpenMP. MP. Okay. So, but if this capacity is not enough for you to solve your problem, that might be different clusters that are available for you to use. And here, OpenMP and MPI, they can help. But if you keep increasing the number of clusters, especially if suppose these clusters over different countries. Here in Europe, where I'm living and working, we can use clusters which are distributed countries in Europe. This could be in France, this could be in Germany, this could be in the Netherlands. And this is MPI and OpenMP will not help you to use these resources. It's only by using a special software that is installed on the cluster. It has to be installed here, here, and here, and we call it grid software, that you as a user are able to simulate these things over the grid. So you can hear, this is you can submit your job here, 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 and they will be all executed, they all belongs to you, and this is made available by grid technology. The difference between the difference between the grid and the cloud is just the difference in abstraction or a there's a bit of noise now. I hope I answered the questions, but I think
I have muted everybody. Adam, you can unmute yourself.
yes. I'm gonna just continue with the central control because this is something that the central control is none of the concern of the user. So you, user, writing program, the only thing you will see, the absence of central control, is that your job is not always guaranteed to be executed directly. So when you submit your job on the grid, it might be executed in 1 minute, and then you just submit, pop, it goes, it's executed. But it can also stay in the queues of these machines for 5 minutes, 10 minutes, 1 day, 2 days. Because you want this software here, the grid here, which has been developed, has no control on this. He cannot take your job and put it on the beginning of the queue. He just put it at the end of the queue, and you have to wait your time up to the top of the queue to go to the resource. And that's what I mean. So it is not really relevant to the user to know about central control, non-central control. The only impact he will see delays in this execution time. So if your application is time critical, that means you're, for instance, doing monitoring of parameter of let's say a dike or the bar, I don't know how they forgot it. Yeah, the dikes. That is, if you, or you're trying to do some forecasting for the weather, and you want to get some result within a minute because you want to tell the weather in 1 hour or 2 hours, and if your job go to the grid and stay 6 hours, then it's not good. So the grid is not for you. So all time critical application will not run efficiently on the grid because they will not, there's no guarantee that the job will be finished on time. I think that was my answer. I think what we can do, what I would like to hear from you guys is that maybe if you can tell us offline what you have questions, and I can also try to answer them next time.
Okay, I unmuted everybody again. Mute all. Yeah.
C'est juste si le pour les habitudes. Voilà, je clique sur.
No, we have noise. Anyways, we're gonna stop here.